to our channel. So today we will discuss about the moving coil galvanometer, which is one of the important topic for your CBSE board examination. We are going to discuss what is meant by moving coil galvanometer, its principle, the construction, working and theory, sensitivity, advantages and disadvantages, and also how to convert galvanometer into ammeter and voltmeter. A moving coil galvanometer is a device to detect the presence of current. It is named so because it uses a moving coil which is kept in a uniform magnetic field due to the torque experienced by it. And this is the principle of a moving coil galvanometer. Whenever a current carrying coil is kept in a uniform magnetic field, that coil experiences a torque. Construction of a moving coil galvanometer. Here we have the top view as well as a front view of the galvanometer. So we will discuss the parts of the galvanometer one by one. But the first part is a rectangular coil. So here is a rectangular coil. Rectangular coil is made up of fine insulated copper wires which is wounded over a non-magnetic but metallic frame. Usually an aluminum frame is used in a galvanometer. So the rectangular coil is nothing but the fine insulated copper wire which is wounded over an aluminum rectangular frame. Now the second part of this galvanometer is the hairspring. Actually this coil, the rectangular coil, is attached to a hairspring. Here is the hairspring, a pair of hairspring, where one end of the hairspring is soldered to the ends of the coil and other ends of the hairspring are soldered to the screw. This hairspring is made up of phosphor bronze. Usually we prefer the material of the hairspring as phosphor bronze because it increases the sensitivity of the galvanometer. What is the function of the hairspring? The hairspring provides the restoring torque and it serves as the current lead. Now the third part of the galvanometer is the aluminum pointer. The pointer is also made up of aluminum pointer. Here is the aluminum pointer. Here you can see the aluminum pointer. The pointer is used to measure the deflection which the galvanometer produces using a linear scale. So the pointer, we are using the pointer in order to measure the deflection produced by the galvanometer while it detects the current. The fourth part of the galvanometer is the permanent magnet. So here is the permanent magnet, where the coil, the rectangular coil, is always placed in between the concave poles of a cylindrical permanent magnet. Usually horseshoe magnet are preferred for the construction of a moving coil galvanometer. So the horseshoe magnet, they are having the concave poles, they are cylindrical in shape. Now the fifth part of the galvanometer is the soft iron core, which is mounted in between the cylindrical poles and the rectangular coil of the moving coil galvanometer symmetrically to the rectangular coil. This soft iron core, due to the presence of this soft iron core, the magnetic field lines always points towards the radius of a circle. Or we can say that the plane of the coil will be always parallel to the magnetic field in all its position. And such a field is known as radial magnetic field. So most important thing regarding the moving coil galvanometer is the magnetic field inside the moving coil galvanometer, and that is nothing but the radial magnetic field. In such a magnetic field, the plane of the coil will always remain parallel to the magnetic field in all its position. And also the soft iron core has high permeability. Due to its high permeability, it intensifies the magnetic field, the radial magnetic field inside the moving coil galvanometer. As a result, it increases the sensitivity of the moving coil galvanometer. Now we will discuss the theory of a galvanometer. How does it work? So for that we are considering a rectangular coil PQRS, which is kept in the strong magnetic field. There is a north pole and there is south pole. Now, according to Fleming's left-hand rule, definitely each side experiences a force because a current carrying coil is kept in a magnetic field. So the force experienced by PS and RQ will be equal and opposite. As a result, they cancels each other, where PQ experiences an outward force and RX experiences an inward force. So there will be a couple of force which causes a rotation of the coil, or that couple of force constitute the torque. So we can say that the coil in a uniform magnetic field experiences a torque. Now suppose I is the current carrying by the coil. A and B are the length and breadth of the coil. Therefore, area of the coil is equal to A into B. Let theta be the angle between magnetic field and normal to the plane of the coil. So here we consider I as a current, A and B as the length and breadth of the coil. Therefore, A into B, side into side, is the area of the rectangular coil, and theta is the angle between the magnetic field and normal to the coil. So here we can say that this coil experiences a torque, and the equation for torque is nothing but force into perpendicular distance. So instead of force, we can write it as IBB, current into length into magnetic field. This is the expression for force experienced by a straight current carrying conductor which is kept in a uniform magnetic field, where B is the length of the coil. So length of PQ and RS is nothing but B. So IBB into the perpendicular distance. Here is the perpendicular distance. Perpendicular distance is nothing but A sine theta. Here B into A can be written as area of the coil. So this is IAB sine theta. So if there are n number of turns for the coil, then the torque experienced by the rectangular coil is NAIB sine theta. So this is a torque experienced by a rectangular coil, NIAB sine theta. In the case of a moving coil galvanometer, the magnetic field inside the galvanometer is a radial magnetic field. That means the plane of the coil always remains parallel to the magnetic field in all its position. So if the plane of the coil is always parallel to the magnetic field, then the normal drawn to the plane will be always perpendicular to the magnetic field. As a result, theta becomes 90 degree because normal is always perpendicular to the magnetic field. Theta is the angle between normal drawn to the plane and the magnetic field. So this torque becomes NIAB, which is the maximum torque. So in a moving coil galvanometer, the rectangular coil which is kept in a radial magnetic field always experiences a maximum torque. So the rectangular coil experiences a maximum torque in the radial magnetic field. As a result, the coil may deflect through an angle alpha. Let alpha be the angle through which the coil deflects due to the torque experienced by it. Due to the elasticity of the hairspring which is attached to the rectangular coil, the hairspring provides a restoring torque. So this restoring torque is directly proportional to the deflection alpha. Restoring torque is directly proportional to the deflection alpha, or the restoring torque is equal to K alpha, where K is known as the torsion constant. So here we got the equation number 2. Equation number 2 is the equation for restoring torque. Restoring torque is equal to K alpha, where K is the torsion constant and alpha is the deflection. At equilibrium, this deflecting torque will be equal to the torsion restoring torque. The deflecting torque will be equal to the restoring torque. So we can equate 1 and 2. At equilibrium condition, the 1 and 2 will be equal. So K alpha is equal to NIAB, or alpha is equal to NAB divided by K into I. Or we can say that alpha is proportional to current I. The deflection is proportional to current I. As the current increases, the deflection increases. As the current decreases, the deflection also decreases. From this equation, we can arrive at an expression for current I, where Just rearranging this equation, we will get an expression for I. I is equal to Kn divided by NAB into alpha, where K is a constant, torsion constant, N is the number of turns, A is area of the coil, and B is the magnetic field. So we can say that K by NAB is a constant. Or I can write this constant as I is equal to G alpha, where G is known as the galvanometer constant. Figure of merit of a galvanometer. It is the amount of current required to produce a deflection of one scale division in a galvanometer. So here we got the equation for current I. I is equal to K divided by NBA into alpha, where alpha is a deflection. So figure of merit is I divided by alpha, that is a current required to produce a deflection of one scale division in the galvanometer. So from this equation, I by alpha is nothing but K divided by NBA, where K is the torsion constant, N is the number of turns, B is the magnetic field, and A is the area of the coil. Sensitivity of a galvanometer. The galvanometer is said to be highly sensitive if it produces a large scale deflection when a small current or a small voltage is passing through it. So first of all, we will discuss about the current sensitivity, where current sensitivity is denoted by IS. Current sensitivity is the deflection produced by the galvanometer when a unit current is passed through it. So current sensitivity is alpha divided by I. The deflection produced in a galvanometer when a unit current is passed through it. Or I can write this as NBA divided by K. Similarly, we will find the expression for voltage sensitivity. It is denoted by Vs, where voltage sensitivity is the deflection produced by the galvanometer when a unit voltage is allowed to pass through the galvanometer. So alpha is Vs is equal to alpha divided by V, or alpha divided by IR. According to Ohm's law, V is equal to IR. Or we can write the voltage sensitivity as NBA divided by R into K. So here we got the expression for current sensitivity as well as the voltage sensitivity. By observing these expressions, it is clear that the sensitivity is directly proportional to N, B and A and inversely proportional to the torsion constant. So the factors affecting sensitivity are the number of turns, the magnetic field, area of the coil as well as the torsion constant. So we can increase the sensitivity of a galvanometer by increasing the number of turns, but we cannot increase it beyond a limit because the galvanometer becomes bulky and the resistance of the galvanometer increases. So the number of turns can be increased within a limit. The second thing to increase the sensitivity of a galvanometer is to increase the magnetic field, because the sensitivity is also directly proportional to the magnetic field. We can increase the magnetic field by using a strong permanent magnet, that is a horseshoe magnet, and also by introducing or mounting a softened coil in between the poles of the magnet and the rectangular coil. Now, the third one is to increase the area of the rectangular coil. Again, we cannot increase the area beyond a limit. If we are increasing the area of the coil beyond a limit, again the galvanometer becomes bulky and it becomes unmanageable. So we have to increase the area within a limit in order to increase the sensitivity of the galvanometer. Now, the fourth one to increase the sensitivity of a galvanometer is to decrease the torsion constant, because the torsion constant is inversely proportional to the galvanometer. Now, how can we decrease the torsion constant? In order to decrease the torsion constant, we always choose the hairspring made up of phosphor bronze, because phosphor bronze have a less torsion constant. At the same time, we can decrease the torsion constant by providing a suspension. So these all are the factors which the sensitivity depends upon: a number of turns, magnetic field, area, and it is inversely proportional to the torsion constant. The galvanometer have advantages as well as the disadvantages. So first of all, we will discuss the advantages of a galvanometer. Where the first advantage is that the galvanometer is made sensitive. It can be made sensitive by increasing the number of turns, by increasing the magnetic field, and by increasing the area of the coil, and also by decreasing the torsion constant. So this is the first disadvantage of a galvanometer. Now the second advantage is that since the deflection is directly proportional to the current, we can use a linear scale in order to measure the deflection. Third advantage. The rectangular coil is made up of metal. So as a result, due to the presence of eddy current, the pointer comes to rest quickly. So this is a third advantage. Now comes the last advantage is that the galvanometer is always made by placing the rectangular coil in a strong magnetic field. So since the coil is placed in a strong magnetic field, the galvanometer won't be get affected by any external magnetic field. As a result, the galvanometer can be used at any positions. It won't get affected by any external magnetic field. Disadvantages of galvanometer. The first disadvantage is that the sensitivity of the galvanometer cannot be increased at will. It can be increased by the time of the manufacturing only. We cannot increase the sensitivity at our will. The second disadvantage is that the galvanometer is a highly sensitive device. Due to its high sensitivity, the overloading may cause damage in the galvanometer. The hair springs as well as the torsion suspension which is attached in the moving coil may get burnt out due to the overloading. Galvanometer is a device to detect the presence of current, but it can be converted into a meter as well as a voltmeter to measure the current and the voltage across a circuit element. So first of all, we will discuss the conversion of galvanometer into an ammeter. What is meant by an ammeter? Ammeter is a device which is used to measure the current in a circuit. So in order to measure the current in a circuit, the ammeter is always connected in series with a circuit. So if the ammeter is having high resistance, when it is connected in series, the no current passes through ammeter. So we cannot measure the amount of current through that circuit. So ammeter should be of a low resistance. Or I can say that an ideal ammeter should have a zero resistance. So that if the ammeter is having zero resistance, when it is connected in series in a circuit, it can measure the complete current which is passing through the circuit. So ammeter should be a device of a low resistance. Now, in order to convert a galvanometer into a meter, I have to convert this galvanometer into a meter by connecting a small resistance in parallel to the galvanometer. And this small resistance or low resistance which is connected in parallel to the galvanometer is known as shunt resistance, or this condition is known as the galvanometer is shunted. A low resistance connected parallel across a galvanometer is known as shunting, or this low resistance is known as shunt resistance. So if a current I is allowed to pass through the circuit, a small current Ig passes through the galvanometer and the remaining current I minus Ig passes through the shunt resistance. So if G is the resistance of the galvanometer, then I can say that the potential differences across a galvanometer and shunt are same because they are connected in parallel. So potential difference across a galvanometer is Ig into G. According to Ohm's law, the potential difference is current into resistance, which is equal to the potential difference across the shunt. That is I minus Ig into S, where S is the shunt resistance. From this equation, we can find the value of shunt. S is equal to Ig divided by I minus Ig into G. From this equation, we can calculate the shunt resistance, value of shunt resistance that has to be connected in parallel with the galvanometer in order to convert the galvanometer into ammeter of desired range. Now, this shunt resistance has some certain uses. First of all, it can protect the galvanometer from the large current. So if it is connected in parallel to the galvanometer, only a small current is allowed to pass through the galvanometer. The remaining current is passing through the shunt. So shunt can protect the galvanometer from large current. The second use of shunt is to convert the galvanometer into ammeter. And it is also used to increase the range of the ammeter. Thus, by connecting a load resistance in parallel to the galvanometer, we can convert the galvanometer into an ammeter. Galvanometer can be easily converted into a voltmeter. Now, what is meant by a voltmeter? Voltmeter is a device which is used to measure the potential difference across a circuit element. So in order to measure the potential difference, we always connect the voltmeter in parallel or across the circuit element. So if the voltmeter is having a low resistance, there is a chance of a current passing through the voltmeter. So if a current is passing through the voltmeter, we may be not able to measure the complete potential difference across that circuit element. So that the voltmeter is always made as a high resistance device. Since the voltmeter is having the high resistance, no current passes through the voltmeter. As a result, we may be able to measure the complete potential difference across that circuit element. So voltmeter is always a high resistance device. For an ideal voltmeter, the resistance is infinity. Here we will convert the galvanometer into a voltmeter by connecting a high resistance in series with the galvanometer. So here is a galvanometer. By connecting a high resistance in series with the galvanometer, this whole apparatus becomes the voltmeter. If Ig is the current passing through the galvanometer and G is the resistance of the galvanometer, according to Ohm's law, Ig is equal to V divided by the total resistance. Since these resistances are connected in series, the total resistance will be the sum of the resistances. So it is G plus R. Or G plus R is equal to V divided by Ig. Or R is equal to V by Ig minus G. From this equation, we can calculate the value of high resistance that has to be connected in series with the galvanometer in order to convert the galvanometer into voltmeter. So thus we can convert a galvanometer into a voltmeter by connecting a high resistance in series with the galvanometer. So this arrangement can be used in any circuit in order to measure the potential difference across the circuit element. So that's all for today. If you find this video helpful, please don't forget to subscribe, share and like. Thank you for watching me.